Welcome to the dry ice tutorial. One of your jobs with this tutorial is to make sure you watch it carefully so that you come prepared tomorrow for a quick oral quiz. Your group of lab partners will not be given any ice to work with until everyone in your group is able to pass the quiz. So the quiz will be on this tutorial and also on the reading. They have the same exact information in them, but I'm giving you both so that you can learn the way that's best for you. You can use both, you can use one of them. So what is dry ice? Well, dry ice is frozen carbon dioxide. At the temperature you usually experience as a human being, carbon dioxide is normally a gas. This is because the intermolecular attractions between carbon dioxide molecules are very weak. They're not attracted to each other. In order for these weak forces to hold the molecules of carbon dioxide together in the liquid or solid state, they need to be slowed way down or be forced into close contact by pressure. The temperature and pressure of this room provides enough energy for carbon dioxide molecules to overcome their attractions and move about freely as a gas. So a dry ice manufacturer gets these molecules to slow down by using powerful refrigeration units as well as compression chambers, similar to the way we compressed our gases with our syringes. They cool the gas way down and they push it together until the weak forces take over and force the carbon dioxide into the solid state. Water doesn't need that much help in order to turn to a solid. Water turns to ice at temperatures that we're quite comfortable at, not, as long as we're wearing a coat, and we can turn it to ice without putting it under any pressure at all. That must mean that water particles have stronger attractions for each other than carbon dioxide molecules do. We saw with the two liquids lab that water molecules also have stronger attraction for each other than alcohol particles do. Alcohol evaporates quicker than water does. Alcohol is more spread out on a sheet of paper if you put a drop of each liquid onto its surface. Alcohol is less dense than water. All of those things are due to the fact that water has really strong attractions for itself. Particles of water stick together like glue. It's hard to get them apart. It takes a lot of energy. On the other hand, carbon dioxide particles have so little attraction for each other that even the tiny amount of temperature we have in the classroom is enough to blow them apart and turn them to a gas. Let's take a look at a diagram called a phase diagram. Here's a phase diagram. The word phase is just another word for state. All substances have phase diagrams that describe the effects of temperature and pressure changes on the state of the molecules of that substance. So take a look at the point on the graph where 20 degrees meets 1 atmosphere of pressure. Atmosphere is just a unit of pressure that is different than the ones you've talked about so far. Here's 20 degrees. Here's 1 atmosphere of pressure. 1 atmosphere is the same pressure you're experiencing right now because of the air at sea level that's pressing down on you at all times. So if we find where these two meet, this graph, by the way, is taken from a website made in Great Britain, which is why they spell the word vapor funny. We spell it without the U. Vapor means gas. You'll notice that at that point, the state of matter of carbon dioxide is a gas, and this is why you only ever experience carbon dioxide as a gas in your normal everyday life. Even on a really, really cold day, when it's, say, negative 20 degrees Celsius, which is extremely cold, right? On a day like that, if you were standing outside and breathing out, you would see a fog form in front of your face, and you might think, oh, the carbon dioxide I'm breathing out is turning to, a liquid, but it's not. That's actually the water you're breathing out that's condensing in the really cold air. The carbon dioxide is still not cold enough to change out of the gas state. It's still a gas at that temperature. So these are the pressure and temperature conditions of the room right now, 20 degrees and 1 atmosphere. And you'll notice that we are a gas under those conditions. So how is it that I'm able to bring solid carbon dioxide into the classroom? Well, it's because I brought it to you from a company that put it under pressure and put it into a refrigeration unit, but the minute I bring it into the room, it's beginning to change right back to a gas. That's because it can't turn to a liquid at this pressure. Check it out. Look at this pressure at 1 atmosphere. Notice how we never, no matter what temperature we go to, we never pass through the liquid phase, which is up here. Which is why carbon dioxide, when it's frozen, is referred to as dry ice. It never melts at normal pressures. It's incapable of being a liquid unless you get the pressure a lot higher. And so this is very convenient if we want to, say, ship something that needs to stay cold over a long distance and we want to pack it in ice, but we don't want the ice to melt. So we can pack it in dry ice, and it will turn directly to a gas over a period of a few hours or a few days. And as a result, we can keep it nice and cold without making a big mess. One of the experiments you're going to do with the dry ice is going to be to force it into a liquid state. You can do this by changing the pressure in a small area, and we're going to use a small pipette to do that. This is the experiment we're going to do where we're going to turn our dry ice into a liquid. And I'm going to do it for you as a demonstration in small groups. So I'll be calling you up to my desk to do it on my desktop. And basically all that I do is I cut off the end of one of our little plastic pipettes, and I stick a small piece of dry ice in there, and then I will clamp it shut with a special tool that I'll show you. And I'll just hold it with my hand, and as the gas builds up inside, because the dry ice is turning to a gas all the time, as it does that, it will increase the pressure inside of that pipette, and as the pressure builds up, that will encourage it to change state to a liquid. So that's pretty cool. We'll watch it kind of like bubble and boil in there, and it's really neat. Incidentally, the state change of going directly from a solid to a gas is called sublimation or subliming. When a substance sublimes, it's skipping the liquid phase because of the pressure and temperature conditions. And it happens pretty often, you just don't notice it. Water does it all the time. It's just hard to notice that a solid piece of ice is evaporating into the air before your eyes because you can't see a gas. However, it's more noticeable with the dry ice because it happens much more quickly, because the ice is so cold compared to this room that it's really like almost like boiling away in front of your face. You'll see too that dry ice has this interesting smoky look to it, and we need to talk about that. You can see from this close-up picture of the dry ice that it appears to be smoking. In fact, it's not smoking, it's making a fog, and this is the same fog that they use on movie sets or when they do a play. What's basically happening here is that the dry ice is turning to a gas, and that gas is invisible. You're not seeing tendrils of carbon dioxide gas floating away. Sorry, I was trying to draw. Right? These are not tendrils of carbon dioxide gas. That's actually fog made of water. Where'd the water come from? Well, the water was in the air. You don't realize it, but the air is full of water or moisture, right? Or humidity. Even in the winter, when you don't think that there's much humidity, there's always some. So the air has lots of water particles as a gas. You're breathing them out all the time into the air from your exhales. So the water molecules in the air are a gas, but if they get too close to this really, really cold ice, they'll slow down and condense into a liquid. So what you're seeing is everywhere we take the dry ice, the air right around the ice gets cooled off and turns whatever water happens to be in it into a fog or a cloud of liquid. So the dry ice is not, you're not seeing carbon dioxide gas coming off it. You're not seeing that. You're seeing water form around your dry ice. And you'll also see that water molecules sometimes freeze directly onto the ice because it's so darn cold that a piece of water floating in the air that bumps into that actual ice block will freeze right onto it like frost. And that state change is called deposition or depositing, which makes sense, right? It's like the water's depositing itself to a surface. You'll notice when I bring the box into the room, you'll look at the box where the ice is and you'll see it's covered in frost because water molecules from the air hit that cold, cold box and immediately turn to a solid. And finally, the dry ice safety rules. Here's the deal. You need to wear your goggles at all times just in case there is an accident with something popping or exploding from ice being put inside of it. Ice should never be put inside of a container that can explode, but that doesn't mean it can't happen. So you need to wear your goggles. You don't want the ice to be exposed to your skin for any length of time. It can touch your skin, but it can't touch it for an extended period of time. And you'll know if it's on there for too long because it'll start to hurt and you'll want to stop touching it. It can cause frostbite if you continue to touch it past where it hurts. It seems like common sense to me, but I feel like it's required that I tell you that you don't want to hold the ice until it begins to hurt. If it starts to hurt, drop it. Absolutely never eat or swallow the ice. It's not that it's toxic or deadly, it's just that it's really, really cold and it could cause frostbite on the way down. It also will expand in your stomach as it turns to a gas, and this can cause your stomach to actually burst. Never put dry ice in an airtight container like a water bottle that can't expand very much, because the water bottle could explode. And you might think that's no big deal because the water bottle's made of soft plastic, but believe it or not, when that plastic is moving at high speed, it is dangerous shrapnel and can cause a lot of damage. If you feel dizzy during the lab, it might be because we are replacing the oxygen in the room with carbon dioxide gas. Carbon dioxide gas is not poisonous or dangerous, but you need oxygen to breathe. So if most of the oxygen in the area of your mouth is replaced with carbon dioxide, you may start to feel a little dizzy because you're not getting very much oxygen. It's not going to kill you or anything, but you should probably go somewhere where there's fresher air, near the back door, where you can open the door a little and just get a quick breath of air, or you could walk out of the classroom for a second or two. I will be ventilating the classroom, so this shouldn't be a problem, but I just want to make you aware of it. And finally, if you remove ice from my classroom, or if you fool around with it, putting it down people's shirts and things like that, I take that very seriously, and I will advocate that you be suspended for behavior like that because it's really, really unsafe. Don't take the ice out of the room where I can't supervise what you're doing with it. Under no circumstances should you put it in somebody else's food or drink, and absolutely, I expect you to be mature with the ice, or you will get yourself suspended. Okay, on that note, if you want your own ice, here's what you do. You can look up places that make and sell dry ice in the Yellow Pages. The place that I use is called Tulo Ice. They're very, very nice. They are in Hasbrook Heights, New Jersey. They are a commercial ice producer, so they normally sell large amounts of ice to businesses. However, you can show up and they will give you a box of ice, which is what I do every year. I show up very early in the morning and ask them for a box of ice, and they're very nice about it. So if you would like to buy ice from them, I'm sure they would be happy to give it to you. You should probably call in advance and ask how much it is and what time you should pick it up and stuff like that. But it's not a regulated substance. It's perfectly legal for you to have it. And if you want to have it, the only recommendation I would make is that you definitely ask your parents, because they have your best interests at heart. And I hope you get an opportunity to play with the ice, not just in my class, but at some point in the future. I certainly enjoy playing with it, and I know you guys will too. Okay, see you in lab. Go to the Yellow Pages and look up dry ice. You will find lots of companies like Tulo Ice, which is where I usually get mine, and you can order some, you can go pick it up. It's not that expensive. It's about $40 for a box the size that I brought into the classroom for the lab. So if you want to get your own ice, talk to your parents and maybe you can get some. Again, the safety rules should apply and you should definitely be supervised by an adult. Okay, see you guys in class for the lab.